Hello, my friend, and welcome. Tonight, we are stepping into one of the biggest stories we can possibly tell. The story of how our solar system began, changed, and became the place we call home. It is a story about fire, motion, destruction, survival, and the quiet forces that shaped everything around us long before we were here to look up at the sky. And the more closely you follow that story, the more you begin to feel that the world around you is part of something far older and far stranger than it first appears. Some of the most familiar things in your life were shaped by events so ancient and violent that they almost feel impossible to imagine. If you have trouble falling asleep, then you are in exactly the right place. So settle in, get comfortable, and let this long journey through the history of our solar system carry you gently away from the day. Chapter 1. Before the sun, there was only a cloud. The story of our solar system begins in a place so quiet and ancient that it can easily be missed, and yet almost everything you know, from the sun above you to the ground beneath you, was hidden there in advance. Before there was a sun, before there were planets, before there was Earth, there was no familiar sky. There was no morning, no sunlight, no orbiting worlds, and no warm center holding everything together. The beginning was far less dramatic to the eye than people often imagine. It was not a bright explosion in empty space, and it was not a sudden instant in which the planets appeared ready-made around a newborn star. It was a cloud, cold, diffuse, and almost invisible, drifting within the Milky Way. This was a molecular cloud, a region where much of the hydrogen existed as molecules rather than single atoms. Such clouds are among the coldest and densest places in interstellar space. They are not dense by everyday standards. Even their thicker regions are far emptier than anything we would call dense on Earth. But in space, where most regions are extraordinarily empty, a molecular cloud contains enough matter for gravity to begin shaping the future. The material inside that cloud was not new. Most of its hydrogen had existed since the early history of the universe, while heavier elements such as carbon, oxygen, silicon, magnesium, and iron had been forged inside older stars. Some stars released those elements gently near the ends of their lives. Others returned them to space through violent stellar explosions. In that sense, the cloud that gave rise to our solar system was an inheritance. It contained the remains of earlier stars mixed with simpler matter from the deep past. That is one of the most remarkable parts of this story. The solar system did not begin from pure, untouched material. It began from recycled matter. The iron in Earth's core, the oxygen you breathe, the silicon in rocks, and the carbon that makes living chemistry possible were all part of a much older galactic cycle. Our system was built from ingredients shaped by events that happened long before the sun itself existed. Inside a molecular cloud, conditions are calm in one sense and unstable in another. The gas is cold, which means its particles move more slowly than they would in hotter regions. Heat creates outward pressure, so colder gas resists collapse less effectively. Gravity, meanwhile, is always working. In most regions of space, that pull does very little because matter is too spread out. But in a cloud that is large enough and cold enough, there comes a point when gravity can begin to win. A cloud does not usually collapse all at once for no reason. Something must disturb the balance. In some regions, nearby stars compress the gas with radiation and winds. In other places, the shock wave from a supernova passes through and squeezes parts of the cloud. Sometimes clouds collide, or large flows of gas inside the galaxy gather matter into denser filaments. Whatever the exact trigger was in our case, one region of the cloud that would one day become our solar system crossed a threshold. It became too dense and too unstable to remain as it was. Once that happened, gravity stopped being just a quiet background influence and became the main force guiding the future. A denser region within the cloud began to contract inward. As it contracted, it drew in more material. The more matter gathered, the stronger the pull became. The stronger the pull became, the faster matter fell inward. A slow drift turned into collapse. It is easy to picture collapse as something sudden, but in space it often unfolds with a strange mixture of force and patience. At first, the region would still have looked dark and dusty from the outside, wrapped in material that blocked visible light. Yet deep inside, change was accelerating. As gas fell inward, gravitational energy was converted into heat. The center grew denser and warmer. A future star was beginning to form, still buried inside the cloud that fed it. The cloud itself was not smooth. Molecular clouds contain denser cores, loose outer regions, turbulent motions, magnetic fields, and thin filaments where matter can pool. Modern observations of star-forming regions show that stars often emerge from these dense structures where gravity can gather material efficiently. That means the origin of our solar system was not a perfect sphere shrinking evenly from all sides. It was a complicated environment shaped by motion, compression, and local variations in density. Dust played an important role in this early stage. Interstellar dust grains are tiny solid particles made of silicates, carbon-rich material, and in some settings, icy coatings. They are far smaller than grains of sand, but they matter enormously. Dust helps clouds cool, blocks visible light, and later becomes the starting material from which larger solid bodies begin to grow. Some of the strongest evidence for this ancient beginning comes from meteorites. A few contain tiny mineral grains that formed before the solar system itself. These pre-solar grains have distinctive isotopic patterns showing that they were created in other stars and survived the birth of our system. Their existence tells us that not everything from the older galactic environment was erased when the sun formed. At this point, there was still no true sun. There was only a dense central concentration forming inside a collapsing region. But another crucial ingredient had already entered the story: rotation. Even if the original cloud turned only slightly, that small motion would matter more and more as the cloud contracted. When a rotating region shrinks, its spin increases. As material fell inward, the growing central object spun faster, and the infalling matter increasingly settled into a flattened disk around it, rather than dropping straight in from every direction. That disk would later become the birthplace of the planets. But even at this early stage, the basic architecture of the solar system was already beginning to appear. The sun would form at the center because most of the mass fell there. The planets would form from the surrounding disk because not everything could fall directly inward. The broad shape of the system was being sketched before any planet yet existed. There is something deeply reassuring about that idea. The solar system did not need a special intervention to organize itself. It followed from simple rules acting over immense stretches of time. Matter gathered, gravity strengthened, motion reshaped the collapse. Heat rose in the center. Dust and gas spread into a disk. Step by step, a star system emerged from conditions that at first seemed shapeless and empty. yet the cloud was never truly empty. In the darkest parts of interstellar space, simple molecules such as water, carbon monoxide, ammonia, and methanol can form on dust grains or in the gas itself. This does not mean life was waiting inside the cloud in any direct sense, but it does mean that the chemistry of the future did not start from nothing. Even before the sun existed, some of the raw materials for rocks, atmospheres, oceans, and later chemical complexity were already present. The environment around the forming solar system was probably not isolated either. Evidence suggests that the sun may have been born in a cluster of stars rather than alone. Many stars form in groups, emerging from the same giant cloud complex at roughly similar times. If that was true for our sun, then nearby young stars may have influenced the early solar system through radiation, stellar winds, or close gravitational encounters. This helps us picture the beginning more accurately. The solar system did not appear as a neat private event in a silent corner of space. It was one chapter in the larger life of the Milky Way. Clouds formed, stars lived and died, new clouds were enriched, denser regions collapsed, and new stars began again. Our sun emerged from that wider galactic recycling process, and the planets emerged from the leftover material surrounding the young sun. And still, for all that vastness, the beginning was physically delicate. A small change in density, a passing shock wave, a slight difference in rotation, or a different local environment could have led to a different outcome. Some clouds never form stars. Some collapsing regions produce several stars instead of one. Some young stars lose much of their disks early. Our solar system was not guaranteed in its exact form. We understand the broad outline with confidence. Stars form inside collapsing molecular clouds. Disks form around young stars. The solar system contains material inherited from earlier generations of stars. Meteorites preserve evidence from those earliest times. And before there was sunlight on Earth, before the planets had names, and before the sky looked anything like the one we know, there was a cold region of interstellar matter waiting for gravity to gather it into something new. So when you picture the beginning of the solar system, there is no need to imagine a polished creation appearing all at once. Imagine darkness threaded with faint structure. Imagine dust too fine to feel and gas too thin to breathe. Imagine ancient atoms carrying the memory of long-dead stars. Imagine a region so cold and quiet that change seems almost impossible until gravity, with immense patience, begins to draw everything inward. From that slow inward drift, all the later drama would come. The sun, the planets, the moons, the asteroids, the comets, the oceans, the rocks, and eventually every living thing on Earth were still hidden in that unformed state, waiting inside a cloud that did not yet know what it was becoming. And perhaps that is a gentle thought to end on. Even the order of our world began in darkness, and even the familiar things around us were once part of something vast, silent, and unresolved. As you let the day soften and drift away, you can rest in that slow beginning, in the calm of the cloud before the sun, where everything was still quiet and everything was still possible. Chapter 2. How the sun was born from collapse. The birth of the sun was not a single instant, but a long transformation in which gravity turned a dark, collapsing region of space into the star that would one day light every world around it. By this point in the story, the future solar system was no longer just part of a cold cloud drifting through the galaxy. One region within that cloud had already begun to fall inward under its own gravity. Matter was gathering toward the center, and the central region was becoming denser and warmer. But a true star still did not exist. What existed instead was a growing concentration of gas and dust hidden inside a larger envelope of infalling material. Stars are not born ready-made. A star begins as a struggle between gravity and pressure. When too much matter gathers in one place, gravity pulls inward more strongly than the gas can resist. Collapse comes first. Light comes later. As material moved inward toward the center, it did not all arrive in a neat, orderly way. Some gas came from denser nearby regions. Some carried more turning motion than the rest. Magnetic fields also helped shape the flow. The process was complicated, but the result was simple. The center became the deepest part of the system, and more material kept falling toward it. As the central region contracted, its density rose sharply. That mattered because dense gas traps energy far better than diffuse gas. In the earliest phase, some of the heat produced by collapse could still escape outward, but as more material piled up, the center became increasingly opaque. Energy had more difficulty getting out, so heat began to build more efficiently. The future sun was still not powered by its long-lasting stellar engine, but it was already becoming hot and luminous because collapse itself releases enormous energy. This early object is called a protostar. A protostar is not yet a fully mature star powered mainly by sustained hydrogen fusion in its core. It is a star in formation, a growing body still being assembled by infalling matter. Its brightness comes mostly from gravitational contraction and from the impact of gas falling onto the protostar or into the hot inner regions around it. That can feel surprising because most of us think of stars as objects that shine simply because they are stars. But before nuclear fusion becomes the main source of energy, gravity can already make a forming star glow. When vast amounts of gas fall inward, gravitational energy is converted into heat. The sun, before it truly became the sun, first shone because it was collapsing. Rotation now became crucial. Even a slight original turn in the collapsing region grew more important as the system shrank. When a rotating cloud contracts, its spin increases. Because of that, not all of the gas could fall straight into the center. Much of it settled into a flattened rotating disk around the growing protostar. This disk was not a minor detail. It was a natural consequence of collapse in a rotating cloud, and it shaped everything that followed. The central protostar held most of the mass, but the disk stored some of the material and much of the system's angular momentum. It also controlled how the protostar continued to grow. Gas from farther out often moved through the disk first, gradually spiraling inward before being added to the young sun. The sun was therefore born through accretion, meaning growth by gathering surrounding matter. This process may sound gentle, but it was energetic. Gas in the disk rubbed, compressed, heated, and slowly lost the ability to remain in the same orbit. Bit by bit, some of it drifted inward. When it finally reached the protostar or the hot region close to it, the release of energy could be intense. Young protostars are often hidden from ordinary view because they remain wrapped in dusty envelopes. Dust blocks visible light extremely well, which is why the earliest stages of stellar birth are hard to see directly. But the object is far from quiet. It radiates strongly at longer wavelengths, revealing that something powerful is taking shape inside the cloud. Another striking feature often appears at this stage: jets. Young stars commonly launch narrow streams of gas outward from their poles at high speed. These jets are linked to the interaction between the rotating disk, the protostar, and magnetic fields. While matter falls inward through the disk, some of it is redirected outward along magnetic pathways and expelled into space. This actually helps the forming star, because the jets carry away angular momentum and make it easier for more material to continue moving inward. So the young sun did not grow in silence. It likely flared, brightened, and expelled matter while still gathering mass. The environment around it was active and turbulent. Inward collapse and outward ejection were happening together. Inside the protostar, temperature and pressure kept rising as gravity compressed the gas more tightly. At first, pressure did not stop collapse. It only slowed it. Gravity still pushed inward more strongly than the hot gas could resist. A stable star requires a long-term balance between these opposing effects, and that balance had not yet been reached. The gas inside was by now so hot that atoms could no longer remain whole. Electrons and atomic nuclei moved separately in a state called plasma. This is the normal state of matter inside stars. Even before the sun reached maturity, it had already become a hot plasma sphere governed by gravity, pressure, radiation, and magnetic activity. Before ordinary hydrogen fusion took over, another brief source of nuclear energy may have played a small role in the deep interior: the fusion of deuterium, a heavier form of hydrogen. Deuterium reacts at lower temperatures than the main hydrogen reactions that power long-lived stars. It did not provide the sun's lasting energy supply, but it may have slowed contraction for a time. The decisive threshold still lay ahead. The core had to become hot and dense enough for sustained hydrogen fusion to begin. That was the great turning point. When the core finally reached the necessary conditions, hydrogen nuclei began to fuse in a stable and continuing way, producing helium and releasing vast amounts of energy. Now the sun was no longer mainly shining because it was shrinking. It had entered the long main phase of stellar life, in which inward gravity is balanced by outward pressure maintained by nuclear fusion in the core. This change was not like a lamp being switched on in a single flash. It was a physical transition into stability, but its meaning was profound. Before this, the object's future depended on continued contraction. After this, it became a true star capable of supporting itself for billions of years. That long balance is called hydrostatic equilibrium. Gravity constantly tries to pull the sun inward. The hot gas and radiation produced inside constantly push outward. Neither side wins completely. Because of this balance, the sun remains stable enough to shine steadily over immense spans of time. At the same time, the newborn sun was not yet as calm as the sun of today. Young stars are usually more magnetically active. They spin faster, produce stronger stellar winds, and release more energetic radiation. The early sun was likely stormier than it is now, and that activity affected the gas disk around it. Radiation, winds, and magnetic processes gradually helped remove material that had not been incorporated into the sun. This clearing phase was crucial. Earlier, the protostar had been buried inside a thick envelope of infalling gas and dust. Later, as accretion weakened and outflows became more effective, the surroundings opened up. The sun emerged from its cocoon. The disk remained, but the central star was now the dominant source of light, heat, and gravity in the system. Most of the matter from the original collapsing region ended up in the sun. That is why the sun today contains almost all of the mass in the solar system. The planets, moons, asteroids, and comets together represent only a small leftover fraction compared with the central star. In one sense, the history of the solar system is the history of what remained after the sun formed. The sun's birth also established an important thermal pattern in the surrounding disk. Close to the center, temperatures were high enough that only certain materials could remain solid. Farther out, cooler conditions allowed ices and more volatile substances to survive. This difference later shaped what kinds of worlds could form in different regions. Rocky planets would emerge in the warmer inner system, while the colder outer system would favor the growth of larger icy and gaseous bodies. Once the sun reached stable fusion, the central source of long-term light and heat was in place. The stage was set for the next act of the story. Around the young sun, the disk still circled, rich with dust, gas, and growing structure. Within that disk, future planets were waiting to take shape. So this chapter is not only the story of how a star ignited, it is the story of how the solar system gained a center. Before this, it was collapsing matter without a clear anchor. After this, it had a heart. The sun became the gravitational master of the system, the main reservoir of mass, the source of light, and the force that would influence every object that formed around it. If you imagine that young sun now, do not picture a perfect golden circle hanging in a finished sky. Picture a restless newborn star surrounded by a glowing disk, still active, still shedding matter, still shaping its surroundings. It had not yet become the calm, familiar sun of modern Earth, but it had crossed the crucial threshold. Collapse had become starlight. Chapter 3. From Dust to the First Worlds. After the sun found its long-lived balance, the great question of the solar system changed from how a star is born to how leftover dust around that star can become worlds. Around the young sun, there still remained a broad rotating disk of gas and dust. This was not empty residue or unimportant debris. It was the construction material for nearly everything that had not fallen into the sun itself. Within that disk were silicates, metals, carbon-rich compounds, and farther from the sun, abundant ices. The disk was thin compared with its width, and it was not static. Gas drifted, dust settled, temperatures changed with distance, and countless particles moved through a shared environment shaped by gravity, collisions, and the heat of the young sun. At first, the solid material in that disk was extremely fine. Many grains were smaller than a grain of sand, and some were even smaller than the width of a human hair. Yet these tiny particles mattered because planets do not begin as large rocks. They begin as dust. When grains in the disk collided gently enough, they could stick. Electrostatic forces helped at the smallest scales, allowing tiny particles to cling together and form larger clumps. What seems almost trivial in a household setting became one of the most important creative steps in the history of the solar system. This growth did not happen everywhere in the same way. Close to the sun, the environment was hotter, and only the more heat-resistant materials could remain solid. Metals and rocky minerals could survive there, but substances such as water, methane, and ammonia were more easily kept in gaseous form. Farther out in the disk, where temperatures were lower, icy materials could freeze into solid grains. That difference mattered enormously. In the colder outer regions, there was simply more solid material available because ice could join rock and metal as building matter. This helped the outer solar system build larger bodies more efficiently than the hotter inner system. As dust grains became aggregates, they began to behave differently from individual particles. Larger clumps were less tightly coupled to the gas around them. They settled gradually toward the midplane of the disk, the denser central layer where much of the material circled the sun. This settling increased the concentration of solids and raised the chances of further collisions. Pebble-sized objects emerged, then larger lumps, and in some regions, these solids may have formed dense streams and clusters, rather than growing only one collision at a time. This stage was not easy. Growth from dust to larger bodies sounds natural, but the path is full of obstacles. Some collisions build, others break apart. A body that becomes too large to drift gently with the gas can begin losing orbital energy and spiraling inward toward the sun. In other cases, impacts become fast enough that clumps bounce off each other or shatter. For a long time, this was one of the central puzzles of planetary science. How do you get from tiny dust grains to truly substantial bodies without losing most of the material on the way? The answer now appears to involve both gradual sticking at small scales and rapid concentration of pebbles into denser swarms that can collapse under their own gravity. Once enough solid matter became concentrated in a local region, gravity began to matter in a new way. Instead of acting only through the sun and the disk as a whole, it started binding smaller clumps together into larger self-gravitating bodies. These were planetesimals, the first truly world-like building blocks of the solar system. They were not planets yet, but they were no longer fragile dust clusters either. They were solid bodies large enough for gravity to help them survive collisions, pull in nearby material, and become the seeds of future worlds. We still have echoes of this stage today. Many meteorites preserve material from the earliest era of planet building. Some contain the oldest solids known to have formed in our solar system, and others preserve textures and mineral mixtures that reflect early heating, melting, or simple accumulation in the disk. These objects are like surviving fragments from the workshop floor, revealing that the first solid ingredients appeared very early and that planet building began surprisingly soon after the sun formed. As planetesimals formed, the nature of collisions changed again. A dust grain that hits another dust grain may stick because the forces involved are tiny. But when bodies become large enough, gravity starts increasing the reach of each object. A planetesimal does not just wait to be struck. It can gravitationally attract nearby material, making collisions more likely than simple geometry would suggest. This effect, often called gravitational focusing, allows some bodies to grow faster than others. Once one object gets a little larger, it tends to gather matter more efficiently, and growth can begin to accelerate. This is how the first major differences in size began to emerge. In the inner solar system, where rock and metal dominated the solid inventory, this process produced the first rocky embryos. These were often called protoplanets, and they represented a new level of organization. They were not just piles of loose debris. Many were large enough for internal heating to become important. Some of that heat came from impacts, some came from compression, some came from radioactive elements present in early solar system material. As a result, at least some early bodies began to change internally, separating denser materials from lighter ones and moving away from their original primitive state. Farther from the sun, where ice could remain solid, the same basic physics operated with a greater supply of building material. That does not mean giant planets appeared fully formed in a simple or immediate way, but it does mean that the outer regions had an advantage. There was more solid mass available to build large cores, and once those cores grew enough, they could begin interacting with the surrounding gas in much more dramatic ways. The full rise of the giant planets belongs later in the story, but its foundations were laid here, in the unequal distribution of solid matter across the disk. The growing young worlds did not orbit through a calm, empty system. They shared the disk with gas, pebbles, smaller planetesimals, and rival embryos. Their paths crossed regions of mixed material. Some objects migrated inward or outward because of drag or gravitational interactions. Some regions were crowded and efficient at growth, while others remained sparse or unstable. The earliest solar system was therefore not a neat assembly line in which each planet formed quietly in its final home. It was a dynamic environment in which bodies formed, drifted, interacted, and competed for matter. There is a temptation to imagine that Earth and the other planets were always destined to exist in something like their present forms. But during this chapter of the story, nothing was settled. There were many growing bodies, many possible paths, and plenty of material that would never become part of a planet at all. Some fragments would later remain as asteroids. Some icy bodies would survive in more distant reservoirs. Some matter would fall into the sun. Some would be thrown outward. The solar system was building worlds, but it was also wasting, sorting, and redistributing material on a huge scale. One of the most beautiful features of this stage is that complexity emerged from repeated small events. No single dust collision created a planet. No single pebble mattered very much on its own. But when enormous numbers of particles share the same disk for long enough, patterns appear. Dust settles, clumps grow, swarms form. Gravity takes over. Larger bodies attract more matter. Embryos emerge. In this way, the solar system crossed a threshold from a disk full of ingredients to a system containing the first worlds in recognizable form. By the end of this stage, the solar system still did not look anything like the calm arrangement we know today. The sun shone at the center, but around it there was still a crowded region of building blocks, partially formed worlds, drifting gas, and colliding bodies. Yet a decisive change had occurred. The disk was no longer just a place where matter circled a young star. It had become a place where some of that matter had organized itself into planetary seeds. That is what makes this chapter so important. It is the moment when the solar system first began producing actual worlds instead of raw material. Dust became pebbles. Pebbles helped produce planetesimals. Planetesimals gathered into embryonic worlds. The first architecture of the planetary system began to appear, even though its final design was still far away. And there is something quietly comforting in that progression. Vast things do not always begin with dramatic events. Sometimes they begin with almost invisible particles meeting one another in the dark, again and again, until structure slowly emerges. If you let yourself rest inside that thought, the story becomes gentler. The worlds were not hurried into existence. They assembled patiently, grain by grain, orbit by orbit, in the warm disk around a young sun that had only just begun to shine. Chapter 4. The Violet Age of Fire and Collisions. Once the first planetary bodies had appeared, the solar system entered one of the harshest phases in its history, a time when young worlds were not yet peaceful planets, but hot, unstable survivors moving through a crowded arena of impacts. The early inner solar system was filled with planetary embryos, smaller planetesimals, and leftover debris moving around the sun on paths that were not yet fully settled. Some of these bodies were already large enough to have strong gravity of their own, and that gravity made encounters more frequent and more consequential. Instead of quietly circling forever in separate lanes, many objects perturbed one another, shifted their orbits, and eventually collided. In this era, growth and destruction were often the same process. A world could become larger because it swallowed another body, but it could also be shattered, stripped, or partly melted by the same kind of event. These were not ordinary impacts like the craters seen on modern Earth from much smaller asteroids. The collisions of the early solar system often involved bodies hundreds or even thousands of kilometers across. When worlds of that size struck one another, the energy released was extraordinary. Rock did not merely crack. It could melt, flow, and in some cases vaporize. Material could be blasted into space, fall back as molten rain, or gather into orbit around the damaged body. A collision between large embryos was less like a single explosion and more like a planetary scale reworking of both objects at once. Not every impact had the same outcome. Some collisions were relatively slow and led to merging, where two bodies combined into one larger world. Others were glancing blows, sometimes called hit-and-run impacts, in which bodies struck, deformed, exchanged material, and then separated again. Some collisions were erosive, stripping away outer layers and carrying debris into space. The result depended on many details, including the sizes of the bodies, the angle of impact, and their relative speeds. This is one reason the planets ended up so different. Their final forms were shaped not only by where they formed, but by what happened to them during this violent age. One of the most important consequences of repeated impacts was heat. A growing world does not begin as a finished cold sphere. During accretion, the kinetic energy of incoming material is converted into heat. Large impacts can therefore drive enormous melting. On some young rocky bodies, the surface or upper layers may have become global or near global oceans of magma. Not oceans of water, but vast expanses of molten silicate rock. These magma oceans were probably common during the earliest histories of the terrestrial planets and the Moon. They marked a stage when the familiar solid surfaces of rocky worlds had not yet fully formed. This molten state changed the internal structure of young worlds. When a body is partly or largely molten, dense materials can move downward more easily, while lighter materials rise. That process is called differentiation. It is one of the defining steps in planetary evolution. On Earth, for example, iron and other dense metal-rich materials sank toward the center to form the core, while less dense silicate material remained above to form the mantle and later the crust. Something similar happened on other differentiated bodies as well. In other words, the violence of early impacts did not only scar worlds from the outside, it helped organize them from the inside. This is why the age of collisions was also the age in which planets acquired their layered interiors. A core, mantle, and crust do not appear automatically just because a body is large. They emerge because material is heated enough to separate by density. Once metal sinks inward, it can create a central core. Once lighter melts rise or crystallize near the top, a primitive crust can begin to form. Many of the internal differences that still define rocky planets today were established during this fiery interval, when impact heating, radioactive decay, and gravitational compression together made young worlds mobile and partially molten. Smaller bodies were affected too. Some early planetesimals appear to have melted and differentiated on a lesser scale, only to be broken apart later. A remarkable clue comes from meteorites. Some are fragments of primitive bodies that never melted much, while others are pieces of differentiated parent bodies, including metal-rich meteorites that likely formed in the cores of once larger objects. That means some early worlds began the process of becoming more complex, only to be destroyed before they could survive as planets. The solar system did not simply build upward toward the worlds we know. It also produced many failed or broken worlds along the way. Among the planets that did survive, impact history may explain some of their strangest traits. Mercury, for instance, has an unusually large metallic core compared with its overall size. One possible explanation is that one or more giant impacts stripped away part of its outer rocky layers, leaving behind a body enriched in metal. That is not the only idea scientists consider, but it shows how early collisions may have helped shape planetary identities. Impact history also influenced how much volatile material, such as water and gases, a world could keep. A large impact can remove atmosphere, melt crust, and alter the chemical balance of a planet's surface and interior. Earth itself almost certainly passed through repeated melting and impact restructuring. The leading explanation for the origin of the Moon is that late in Earth's formation, a large body struck the young Earth in a giant impact. The exact details are still studied and refined, but the broad picture is strongly supported. A collision involving the proto-Earth and another planetary body produced debris that later gathered into the Moon. This model helps explain the angular momentum of the Earth-Moon system and the close chemical relationship between lunar and terrestrial rocks. In this view, our Moon is not a captured outsider. It is part of the wreckage of Earth's own violent youth. That event also helps explain why the earliest Earth was probably far more molten than the modern planet. A giant impact of that scale would have delivered immense heat, likely remelting large portions of Earth's outer layers and contributing to a deep magma ocean. The newborn Moon also appears to have experienced a magma ocean of its own before cooling and developing a crust. So when we look up at the Moon as a calm, bright companion in the night sky, we are looking at an object whose origin was probably catastrophic and whose earliest surface was once an ocean of molten rock. The bombardment did not stop with the moon-forming event or with the first round of planetary assembly. Leftover debris remained throughout the inner solar system, and impacts continued for a very long time. The Moon preserves much of that record because it lacks the weather-flowing water and active plate tectonics that erase ancient scars on Earth. Many scientists have proposed that there may have been a later spike or surge in the impact rate, often called the late heavy bombardment, but the exact timing and shape of that history remain debated. What is clear is that the early inner solar system experienced a much higher impact flux than it does today, and those impacts played a major role in shaping planetary surfaces. For Earth, this means the visible record of the earliest violet era is frustratingly incomplete. Our planet is geologically active. Its crust is recycled, weathered, and reshaped by erosion, volcanism, and plate motion. Much of the evidence has been lost or transformed, But the Moon, Mercury, Mars, and many meteorites preserve enough clues to show that the inner solar system once endured a prolonged period of intense collisional modification. Craters, impact basins, melted rocks, shock features in minerals, and disturbed isotopic systems all point to a time when impacts were not occasional interruptions. They were a normal part of planetary life. Collisions also mattered for more than shape and heat. They influenced atmospheres and the delivery or loss of volatile substances. Some impacts may have brought in water-rich material or chemically useful compounds. Others may have blasted gases away, especially from smaller bodies with weaker gravity. This means that early bombardment could both enrich and impoverish a world depending on its size, temperature, and the nature of the incoming bodies. The final habitability of Earth, the dryness of Mercury, and the contrasting histories of Venus and Mars were not determined by impacts alone, but impacts were undeniably part of the story. Over time, the number of large free-roaming embryos declined. Some were absorbed into growing planets. Some were broken apart. Some may have been thrown inward toward the sun or outward into more distant regions. As the population of large impactors fell, the inner solar system gradually became less chaotic. The major rocky planets approached their final masses, and the most destructive giant collisions became less common. Solid crusts could persist for longer. Magma oceans cooled. Separate layers inside the planets became more stable. The era of endless planetary reconstruction slowly gave way to one of longer-term evolution. Still, traces of that terrible youth remain everywhere. Earth's iron core, the existence of the Moon, the battered face of Mercury, the heavily cratered lunar highlands, and the ancient scars preserved on Mars all carry memories of this age. The rocky planets did not emerge as calm spheres placed neatly around the sun. They were forged, melted, struck, stripped, and rebuilt. Fire and collision were not side effects of planetary formation. They were central to it. And perhaps the most important lesson of this chapter is that violence in the early solar system was not pointless chaos. Out of repeated impacts came internal structure, stable survivors, and the final arrangement from which later histories could unfold. The worlds had to pass through a destructive age before they could become the planets we recognize. What feels brutal from a human point of view was, in planetary terms, part of the making. Chapter 5. Why the inner planets became so different. Mercury, Venus, Earth, and Mars were all born in the inner solar system, from broadly similar rocky materials circling the same young sun, and yet they became four profoundly different worlds. At first, that might seem surprising. If the inner planets formed in the same general neighborhood, it is easy to assume they should have ended up resembling one another, perhaps as slightly different versions of the same basic planet. But planetary history does not work that way. A world is shaped not by one factor alone, but by an entire chain of conditions acting over immense spans of time. Distance from the sun matters. Size matters. Internal heat matters. The presence or absence of a strong magnetic field matters. Atmospheric evolution matters. Volcanism matters. Impacts matter. The result is that even planets with related origins can diverge into radically different outcomes. The simplest difference was location. Mercury formed closest to the sun, where temperatures were highest and only the most heat-resistant materials could remain solid during the earliest stages of assembly. Farther out came Venus, then Earth, then Mars. These differences in distance were not enormous when compared with the scale of the whole solar system, but they were enough to create very different thermal environments. A little more sunlight or a little less can change how gases behave, how volatile substances are retained, how quickly surfaces heat, and how atmospheres evolve over time. The inner planets did not begin in identical settings. They began along a gradient. Mercury is the most extreme example of what closeness to the Sun can do when combined with small size and unusual internal structure. It is a rocky world, but not a typical one. Mercury has an extraordinarily large metallic core relative to its total size, and only a comparatively thin outer shell of mantle and crust. Scientists are still working out exactly how this happened. One possibility is that Mercury formed from material already enriched in metal. Another is that one or more giant impacts stripped away part of its outer rocky layers early in its history. What is clear is that Mercury did not simply become a smaller Earth. It followed a more unusual path. Its proximity to the Sun also shaped its surface and atmosphere. Mercury does not have a substantial atmosphere like Earth or Venus. Instead, it has an extremely thin exosphere, a sparse envelope of atoms that are constantly being added and lost. Its weak gravity makes it harder to hold on to gases over long periods, and the intense solar environment further strips and reshapes what little surrounds it. Without a thick atmosphere to redistribute heat, Mercury experiences extreme temperature swings between day and night. It is heavily cratered, geologically ancient in appearance, and exposed. In many ways, it looks less like a living planet and more like a battered remnant of the solar system's earliest ages. Venus and Earth make perhaps the most striking contrast of all, because they are so similar in size and overall rocky composition, yet so different in outcome. Venus is often called Earth's sister planet, and in some broad physical ways that description makes sense. The two planets are close in size, close in density, and likely formed from related kinds of material. Yet today, Venus is an inferno. Its atmosphere is overwhelmingly dominated by carbon dioxide, its surface pressure is crushing, and its temperature is high enough to melt lead. Earth, by contrast, has liquid oceans, a temperate surface, and a chemically active climate system that has remained suitable for life for vast stretches of time. Why did this divergence happen? The deepest answer is that Venus and Earth responded differently to the same broad planetary ingredients. Venus orbits closer to the Sun and receives more solar energy. That does not automatically mean it had to become what it is now, but it pushed the planet toward a more fragile climate balance. If water was present on early Venus, as some models suggest may have been possible, increasing heat would have allowed more water vapor to rise into the atmosphere. Water vapor is itself a greenhouse gas, so this would have trapped more heat, causing further warming. At high enough temperatures, oceans cannot remain stable. Water is lost to the atmosphere, sunlight breaks water molecules apart, and hydrogen escapes into space. Over time, a planet can be left drier and hotter, with carbon dioxide accumulating in a dense atmosphere and driving a runaway greenhouse state. It is important to be careful here, because the full early history of Venus is still not known with certainty. Scientists are still investigating whether Venus had long-standing oceans, how much water it originally possessed, and how exactly its atmosphere and surface evolved together. But the broad picture is strong. Venus and Earth likely began with some meaningful similarities, then diverged because of differences in solar heating, atmospheric evolution, interior dynamics, and long-term climate feedbacks. Venus is not simply Earth with hotter weather. It is a world whose entire surface atmosphere system shifted into a very different state. Earth's path was different, not because it was magically protected, but because several conditions worked together in a favorable way. Earth formed at a distance from the Sun where liquid water could remain stable on the surface once the planet cooled enough. It was massive enough to retain a substantial atmosphere and stay geologically active over very long periods. Its interior remained hot enough to drive mantle motion, volcanism, and plate tectonics. These deep processes helped regulate the carbon cycle over geologic time, moving gases between the atmosphere, oceans, crust, and interior. That kind of long-term recycling is one of the reasons Earth's climate did not lock permanently into either a Venus-like furnace or a Mars-like frozen desert. Earth also possesses a strong global magnetic field generated by the motion of electrically conducting liquid metal in its core. This magnetic field does not create habitability by itself, and life on Earth depends on many interacting systems, but it does help protect the atmosphere from erosion by the solar wind and reduces the direct impact of harmful charged particles from space. That protection is especially important over immense spans of time. Earth's magnetic shield is therefore one more piece of a larger pattern. Sufficient size, sustained internal activity, climate regulation, surface water, and a protective magnetosphere all helped Earth remain a living world. Even Earth, however, should not be treated as the automatic or default result of rocky planet formation. It is better understood as one outcome among several possible ones. A somewhat different early atmosphere, a different rate of volcanic outgassing, a different collisional history, or a different balance of internal heat loss might have altered the planet's path substantially. Earth looks normal to us only because we live on it. In the context of the inner solar system, it may be the most balanced of the 4 terrestrial planets. But balance is not the same thing as inevitability. Mars shows what can happen when a rocky planet begins with some favorable ingredients, but lacks the mass to hold on to them for the longest timescales. Evidence from its surface and minerals shows that early Mars once had abundant liquid water. Rivers flowed, lakes existed, and at least some regions were far more hospitable than the cold desert we see today. The ancient Martian atmosphere was thicker than the current one, and the climate was warmer. This means Mars was not always the dry, fragile world it is now. It changed. A major reason for that change appears to be planetary size and internal evolution. Mars is only about half Earth's diameter and significantly less massive. Smaller planets lose internal heat more quickly because they have less volume relative to their surface area. As Mars cooled, its internal engine weakened. At some point in the distant past, it lost the global magnetic field that once would have helped shield its atmosphere. Without that strong global magnetic protection, the solar wind was able to interact more directly with the upper atmosphere, contributing over time to atmospheric escape. As the atmosphere thinned, surface conditions became colder and less capable of sustaining stable liquid water. What had once been a wetter world gradually became the frozen, arid planet we know today. This does not mean Mars was ruined by a single event. Its transformation was a long process involving atmospheric loss, cooling, changing volcanic activity, and shifts in how water was stored on or beneath the surface. Some water escaped to space, some became locked in minerals, and some froze in the subsurface or polar regions. The important point is that Mars did not fail because it was rocky. It faltered because it was small. It could not remain geologically vigorous and atmospherically robust in the same way Earth did. Seen together, the four inner planets form a kind of natural comparison set. Mercury shows the stripped, metal-rich, atmosphere-poor extreme close to the Sun. Venus shows how a large rocky planet can become overwhelmingly hostile through greenhouse evolution and climatic divergence. Earth shows that a rocky world can remain temperate when distance, size, internal activity, and atmospheric regulation align well enough. Mars shows how habitability can be possible early on and then fade when a planet loses the ability to protect and renew itself. That is why the inner planets became so different. They did not begin as four unrelated stories. They began as variations on a shared theme and then diverged because small differences became large ones over time. A slightly different distance from the Sun changed heating. A different mass changed gravity, cooling, and atmospheric retention. A different interior history changed magnetic shielding and volcanic activity. Different climate feedbacks either stabilized or amplified change. Once those pathways began to separate, the planets moved farther and farther apart in character. So the lesson of the inner solar system is not that rocky planets are simple. It is that they are sensitive. They respond to many influences at once, and over long enough timescales, those influences can produce outcomes as different as a scorched metal-rich world, a runaway greenhouse planet, a blue ocean world, and a cold desert, preserving the memory of lost rivers. The inner planets began near one another, but they did not remain alike. They became a record of how planetary history branches. Chapter 6: The Rise of the Giant Planets. Far beyond the region where the rocky planets were taking shape, the young solar system was building a different kind of world, one so massive that it would not merely orbit the Sun, but help determine the architecture of the entire planetary system. In the outer part of the disk around the young Sun, conditions were colder than in the inner regions. That single difference changed almost everything. Closer to the Sun, only rock and metal could remain solid during the main era of planetary assembly. Farther out, water could freeze, along with other substances such as ammonia and methane. This meant that the outer disk contained much more solid material than the inner disk did. There was simply more building matter available. In planetary formation, that matters enormously, because the more solid material a region contains, the easier it is to build large cores quickly. This is the basic reason the giant planets were able to rise at all. They did not begin as ready-made spheres of gas. They began with solid growth, just as the inner planets did. Dust became larger particles became planetesimals, and planetesimals gathered into growing planetary cores. But in the colder outer disk, those growing bodies had access to a richer supply of solids. Ice joined rock and metal as structural material. As a result, the early cores in the outer solar system could become much larger than the rocky embryos closer to the Sun. This process is usually explained by the core accretion model, which is the leading picture for how the giant planets in our solar system formed. In this view, a growing outer planet first assembled a large solid core. Once that core became massive enough, its gravity could hold on to a surrounding envelope of gas. At first, the gas envelope was modest, but if the core formed early enough, while large amounts of gas still remained in the disk, the planet could begin pulling in hydrogen and helium much more rapidly. At that point, growth changed character. A body that had begun as a solid core could become a giant planet wrapped in a vast gaseous envelope. Timing was crucial. The gas in the disk did not last forever. The young sun and the general evolution of the disk gradually removed it, so a future giant planet had to grow its core quickly enough to capture gas before the supply faded. This is one reason Jupiter and Saturn stand apart from the rocky planets. They were not simply farther away. They formed in the right environment and on the right timescale to gather enormous gaseous envelopes, while the disk still contained abundant hydrogen and helium. Jupiter appears to have been the first of the giant planets to rise. That makes sense, because it is the largest planet in the solar system and contains by far the most mass among the planets. Its core likely formed early, and once it began drawing in gas efficiently, its growth accelerated dramatically. Jupiter became a world dominated by hydrogen and helium, with a deep atmosphere, powerful gravity, and no solid surface in the ordinary sense. If you tried to descend into Jupiter, you would not find a simple boundary where atmosphere ends and ground begins. Instead, pressure would rise, gases would become denser and hotter, and the planet's outer layers would merge gradually into deeper fluid regions. Saturn followed a similar general path, though it did not become as massive as Jupiter. It too is a gas giant, made mostly of hydrogen and helium, and it too likely formed from a solid core that began accreting gas before the disk dispersed. Saturn's lower mass may reflect local conditions, the timing of its formation, or the growing influence of Jupiter itself. The important point is that Jupiter and Saturn represent a distinct class of outer planet. They are giant worlds whose bulk is dominated by the light gases that filled the young solar system. Uranus and Neptune are different. They are also giant planets, but they are not simply smaller versions of Jupiter and Saturn. Their internal makeups suggest that much more of their mass is in heavier materials, including water, ammonia, methane, rock, and other dense components, rather than overwhelmingly in hydrogen and helium. For this reason, they are often called ice giants. The word ice can be misleading here, because deep inside these planets, the relevant substances are not present as ordinary household ice. Under extreme pressures and temperatures, they exist in hot, dense fluid states. But the name still captures an important distinction. Uranus and Neptune contain a larger fraction of these so-called icy materials than Jupiter and Saturn do. That difference raises an important scientific question. If all four giant planets formed in the outer solar system, why did only two become classic gas giants while the other two remained ice giants? The broad answer is that Uranus and Neptune probably grew more slowly or in a different environment, and did not capture as much hydrogen and helium before the gas disk thinned away. Their cores may still have become substantial, but the great gaseous phase did not proceed as far as it did for Jupiter and Saturn. As a result, Uranus and Neptune remained giant planets with thick atmospheres, but not planets dominated to the same degree by the lightest gases. There is still active research on the details. Uranus and Neptune are challenging cases for planet formation models because they are far from the Sun and yet fairly massive. Many scientists think they may not have formed exactly where they orbit today. A growing body forms more easily in a region where material is denser and orbital times are shorter. So one strong idea is that Uranus and Neptune formed somewhat closer to the Sun and later moved outward. That question belongs more fully to the next stage of solar system history, when the planets begin changing places. But even here, it helps explain why the outer planets should not be imagined as having quietly appeared in their final arrangement. As these giant planets grew, they began doing more than simply adding mass to themselves. Their gravity reshaped the disk around them. A planet as large as Jupiter does not act like just another object among many. It disturbs the orbits of nearby bodies, scatters planetesimals, redirects gas flows, and can even open gaps in the surrounding disk. In other words, once a giant planet forms, it begins to influence the entire environment from which other worlds are still emerging. This is one reason the rise of the giant planets is such a major turning point in the story of the solar system. Before them, the disk was building worlds. After them, some of those worlds began to control the disk itself. Jupiter in particular became a gravitational giant in every sense. It likely limited what could form in its neighborhood, redirected countless smaller bodies, and helped shape the boundary between the inner and outer planetary systems. Saturn added further complexity, and together, the giant planets helped define the large-scale structure of the solar system. Their influence extended to smaller bodies as well. Around them, smaller disks of material likely produced systems of moons. In that sense, the giant planets became miniature solar systems of their own, with satellites, rings, and intricate gravitational relationships. Jupiter's major moons and Saturn's rich satellite system are reminders that giant planet formation was not just the growth of 4 large planets. It was the creation of entire local systems around them. The giant planets also preserved something of the early solar system that the rocky planets did not. Because Jupiter and Saturn captured so much hydrogen and helium, they retain a composition that more closely reflects the general material of the young solar nebula. They are not exact copies of the Sun, and they contain important enrichments in heavier elements, but they still carry a record of the primordial gaseous environment in which the solar system formed. Uranus and Neptune, though compositionally different, also preserve evidence about the colder outer regions of the disk and the chemistry available there. And yet, for all their size, giant planets are not failed stars. Jupiter is enormous, but it never became hot and massive enough to ignite sustained hydrogen fusion in its core. The same is true for the other giant planets. They formed through planetary processes inside a disk around a star, not through the direct collapse that forms stars themselves. By the end of this chapter in the solar system's history, the outer regions had changed from a broad, cold reservoir of material into a realm dominated by 4 giant worlds. Jupiter and Saturn had become gas giants, wrapped in immense hydrogen and helium envelopes. Uranus and Neptune had become ice giants, rich in heavier volatile materials and capped by thick atmospheres. Together, they held most of the planetary mass outside the Sun. The solar system now had not only inner rocky planets and leftover debris, but a massive outer structure capable of shaping everything else. This is why the giant planets matter so much in the larger story. They were not decorative additions placed beyond the asteroid belt. They were major agents of order and disruption. Their rise influenced where material remained, where bodies were scattered, what kinds of planets could continue growing, and how the next phase of solar system history would unfold. Without them, the planetary system would have developed very differently. So when you picture the young outer solar system, do not imagine a quiet, dark expanse with a few distant planets slowly circling in silence. Imagine a colder but richer frontier where large solid cores were racing against time, where gas was still available for capture, where Jupiter rose first like a new gravitational force in the disk, and where Saturn, Uranus, and Neptune followed along different paths. In that frontier, the balance of the solar system began to shift. The era of giant planets had arrived, and once it did, nothing else in the system could remain quite the same. Chapter 7. When the planets changed places. It is tempting to imagine that once the planets formed, they simply remained where they were, circling the sun in the same orderly arrangement we see today. But the deeper story appears to be far more dynamic than that. For a long time, the solar system was pictured as a place whose main structure had been fixed almost from the beginning. In that older view, each planet formed more or less where it still orbits now, and the later history of the system was mostly a matter of cooling, cratering, and slow change. But as scientists studied the outer planets, the asteroid belt, and the distant populations beyond Neptune in greater detail, a different picture grew stronger. The planets may not have stayed in their original places. Instead, at least some of them appear to have migrated, shifting inward or outward through the young solar system and reshaping the entire system as they moved. This idea is not strange when you think about how the early solar system actually looked. It was not a quiet clockwork system moving through empty space. It was a young star surrounded by leftover gas, small bodies, and newly formed planets still embedded in a changing environment. In such a setting, gravity does not simply hold objects in place. It causes exchanges of momentum and energy. A planet can push on the disk around it, and the disk can push back. A planet can scatter smaller bodies inward or outward and, in doing so, alter its own orbit. When enough matter is still present, motion becomes part of formation itself. One major stage of planetary migration likely happened while gas still remained in the protoplanetary disk. In that era, the giant planets were not moving through empty space, but through a gaseous medium that could exert torques on them. A growing giant planet disturbs the gas around it, creating density patterns in the disk. Those patterns then pull gravitationally on the planet. Depending on the mass of the planet and the state of the disk, this can cause the orbit to drift inward or outward. Jupiter, which became the most massive planet in the solar system, may have migrated significantly during this early gas-rich stage. One influential model suggests that Jupiter first moved inward toward the Sun and later reversed direction after Saturn formed and entered a particular gravitational relationship with it. In that picture, the two planets then moved outward together. This idea is often called the grand tack, using the image of a sailing boat that turns and changes course. The full details are still being tested, and not every part of the model is certain, but the broader lesson is powerful. Giant planets need not stay where they first formed. If something like that happened, the consequences would have been enormous. Jupiter is so massive that any major change in its orbit would have affected huge amounts of material. An inward-moving Jupiter could have truncated the region where the rocky planets were still assembling, limiting how much material remained beyond the orbit of Earth and helping explain why Mars ended up much smaller than Earth and Venus. Later outward movement could have repopulated certain regions with mixed material from different parts of the solar system. In this way, migration would not have been a side event. It would have helped sculpt the inner solar system itself. That possibility helps explain something that once seemed puzzling. If the early inner solar system contained a broad and smooth distribution of rocky building material, standard models often had difficulty producing such a small Mars. They tended to make Mars too large. A scenario in which Jupiter moved inward and then outward offers one way to naturally reduce the amount of solid material available near Mars's region. It also offers a possible explanation for why the asteroid belt contains a mixture of bodies with different compositions rather than a single uniform population. Still, the gas disk stage was only part of the story. After the gas dispersed, the outer solar system still contained a vast population of leftover icy planetesimals beyond the giant planets. These were smaller bodies, but they were numerous enough that they continued to matter dynamically. When a giant planet gravitationally scatters a smaller body inward, the planet itself tends to recoil slightly outward. When it scatters a body outward, the planet tends to move slightly inward. Over time, repeated interactions with many small bodies can gradually shift planetary orbits. This kind of exchange appears especially important for Neptune. Much evidence suggests that Neptune moved outward through a primordial disk of icy bodies. As it migrated, it gravitationally captured some objects into orbital resonances, meaning patterns in which their orbital periods became locked into stable ratios with Neptune's own orbit. Pluto is one of the most famous examples. It does not wander randomly beyond Neptune. Its orbit reflects a long-term resonant relationship that protects it from close encounters with the giant planet. The existence of many resonant objects in the distant solar system is one of the strongest clues that Neptune did not simply form in its current place and remain there unchanged. As Neptune moved outward, it likely stirred and redistributed the populations beyond it, helping create the structure of the Kuiper belt we see today. Some objects remained in relatively calm, low-inclination orbits. Others were scattered into more excited and tilted paths. Some were trapped in resonances. Some were thrown far outward into the scattered disk. The distant solar system, in other words, carries the fingerprints of planetary migration. Its structure looks less like the untouched edge of a quiet system and more like a region reshaped by moving giant planets. Jupiter and Saturn also appear to have entered powerful gravitational relationships with one another during the early history of the solar system. When planets approach resonances, their mutual gravitational pulls can become especially effective at changing orbital shapes and system-wide stability. In some models, the giant planets began in a more compact arrangement than they have now. Later, as interactions with leftover planetesimals continued, that arrangement became unstable. The planets' orbits shifted, eccentricities increased, and the outer solar system passed through a chaotic transition. This broader framework is often called the Nice model, named after the city in which key parts of it were developed. In that picture, the giant planets did not merely drift smoothly into their present orbits. Instead, the system underwent an instability in which gravitational encounters and resonance crossings caused the outer planets to rearrange themselves. Jupiter moved somewhat inward, while Saturn, Uranus, and Neptune moved outward, Neptune in particular was displaced into the outer planetesimal disk, which it then scattered and reorganized. This kind of instability helps explain several important features of the modern solar system. It can account for the wide orbital spacing of the giant planets, the resonant and scattered populations beyond Neptune, and the existence of smaller body reservoirs such as the scattered disk and parts of the Oort cloud. It also provides a natural mechanism for sending icy bodies inward toward the Sun and redistributing material across large distances. For many years, one open question was when this instability happened. Some older versions of the story connected it to a very late surge in bombardment in the inner solar system. More recent work has often pointed toward an earlier instability, closer to the era of planet formation rather than hundreds of millions of years afterward. That detail is still an area of active research, but the important point for this chapter is that the instability itself is a serious part of mainstream thinking. The exact timing may still be refined, but the idea that the giant planets shifted and destabilized the surrounding system is supported by many lines of evidence. What makes this chapter so important is that migration changes how we understand the solar system as a whole. The planets were not simply passengers moving along tracks laid down at birth. They were participants in a collective gravitational evolution. Their motions influenced one another. Their migrations redistributed smaller bodies. Their resonances carved patterns into the architecture of the system. The present solar system is therefore not just the result of where the planets formed. It is also the result of how they moved afterward. This helps explain why the solar system can look both orderly and scarred at the same time. Today, the planets follow stable, predictable paths. But that calm arrangement may be the final settled outcome of an earlier period of movement and instability. Order did not necessarily come first. It may have emerged after a period in which the planets shifted position, disturbed one another, and swept through regions full of smaller bodies. There's also a larger lesson here that reaches beyond our own system. The discovery of exoplanets has shown that planetary systems can be astonishingly diverse. Some giant planets orbit extremely close to their stars. Others occupy eccentric or tilted paths. This wider context makes migration seem less like an exotic possibility and more like a common feature of planetary evolution. Our solar system may be calmer than some systems, but it was likely not static. It also changed course. By the end of this phase, the main planets were much closer to the arrangement we know today. Jupiter remained the dominant gravitational force among the planets. Saturn settled farther out. Uranus and Neptune occupied the distant outer system. The asteroid belt had been depleted and mixed. The Kuiper belt had been structured by Neptune's passage. Countless smaller bodies had been scattered, captured, or ejected. The solar system had not only formed planets, it had rearranged them. So when we look at the present map of the solar system, we should not see it as a frozen blueprint from the first moment of planetary birth. We should see it as the outcome of motion. Planets grew, but they also traveled. They did not all stay where they began. They changed places, and in doing so, they transformed the destiny of countless smaller worlds around them. Chapter 8: The Leftovers That Never Became Planets. Not every piece of the young solar system succeeded in becoming a planet, and in many ways, the bodies that were left behind are among the most valuable witnesses to how the whole system was made. When people imagine the formation of the solar system, they often picture a straightforward process in which dust gathered into rocks, rocks gathered into worlds, and the finished result was the neat family of planets we know today. But that picture is too simple. Planet formation was never perfectly efficient. A great deal of material was scattered, stranded, broken apart, or prevented from growing further. Some of it remained in belts and distant reservoirs. Some of it survived as dwarf planets, asteroids, comets, and smaller icy bodies. These objects are not just failed planets. They are preserved fragments of the original construction process, pieces of the early solar system that never fully disappeared. The asteroid belt is one of the clearest examples. It lies between Mars and Jupiter, and for a long time people imagined it might be the remains of a shattered planet. That is not the modern scientific picture. The asteroid belt is better understood as a region where a full planet never formed in the first place. The material there was disrupted by the strong gravitational influence of Jupiter, which stirred up the motions of smaller bodies and made gentle accumulation much more difficult. Instead of calmly merging into one large world, many objects collided at speeds too destructive for steady planetary growth. The result was a population of remnants rather than a finished planet. Even so, the asteroid belt is not just a chaotic pile of rubble. It contains a record of different conditions from the early solar system. Some asteroids are rocky. Some are richer in carbon-bearing material. Some contain metal. Their diversity tells us that the early solar system was chemically structured, with different temperatures and materials available at different distances from the Sun. Many meteorites that fall to Earth come from asteroid parent bodies, which means they carry samples of ancient solar system material into our hands. Some are primitive and relatively unchanged, while others come from bodies that once melted, separated internally, and were later broken apart. This is what makes the asteroid belt so scientifically important. It is not only a place where growth stalled, it is also an archive. Its bodies preserve evidence of early heating, collisions, chemical sorting, and internal evolution. The total mass of the whole belt today is quite small, far less than the mass of our moon, which shows that the region is not a hidden planet waiting to be reassembled. It is a depleted population, the thin surviving residue of a much richer early environment. Within the asteroid belt, Ceres stands out. It is the largest object there and the only dwarf planet in the inner solar system. Ceres is especially important because it shows that the line between asteroid and planet-like world is not perfectly sharp. It is round under its own gravity, and it contains abundant water-rich material. In that sense, Ceres is a surviving protoplanet, a body that grew large enough to become something more complex than an ordinary asteroid, but never continued on to full planetary status. Other large asteroids, such as Vesta, tell another part of the story. Vesta appears to have undergone strong internal heating early in its history and developed a differentiated structure, with denser material sinking inward and lighter material remaining above. In other words, some asteroid belt bodies were once on their way toward becoming more geologically complex worlds. Their survival shows that the solar system did not produce only planets and pebbles. It also produced intermediate bodies, some partly evolved, some primitive, many scarred by later impacts. Beyond the asteroid belt, the leftovers become icier and stranger. In the outer solar system, many small bodies survived in regions where the giant planets prevented them from combining into larger worlds. The Kuiper Belt is the most famous of these regions. It is a broad, donut-shaped zone beyond Neptune, filled with icy bodies left over from the early solar system. Like the asteroid belt, it is a leftover population. But unlike the asteroid belt, it formed in a colder environment, so its objects contain much more ice and other volatile materials. The Kuiper Belt is not a thin and simple ring. It has structure. Some bodies move on relatively calm, near-circular orbits. Others travel on more stretched or tilted paths. Some are trapped in resonances with Neptune, meaning their orbits are linked to Neptune's in stable numerical patterns. This is one of the strongest signs that the outer solar system was reshaped by planetary migration. Neptune did not merely sit beyond the Kuiper Belt like a fence post. Its gravity stirred the region, trapped some bodies, scattered others, and helped leave behind the arrangement we see now. Pluto is the most famous object in the Kuiper Belt, but it is not alone. It was once treated as the 9th planet because it was the first body of its kind to be discovered there. But later findings revealed that Pluto belongs to a broader population of distant icy worlds. That realization changed our view of the solar system. Pluto became not a fallen world, but the first recognized member of a much larger class. It is a dwarf planet, large enough for gravity to shape it into a sphere, but still part of the leftover architecture of the outer system rather than one of the dominant planets. Other dwarf planets in the distant solar system, such as Eris, Haumea, and Makemake, reinforce the same message. The solar system does not end with Neptune and then fade into emptiness. It continues into populations of ancient small worlds, many of them large enough to be geophysically interesting, but not large enough or not dynamically favored enough to become major planets. They are survivors from an unfinished zone of planetary formation. Past the main Kuiper Belt lies the scattered disk, a more dynamically excited region containing bodies that were flung onto elongated and tilted orbits, largely through interactions with Neptune. These are leftovers too, but leftovers that were actively displaced during the rearrangement of the giant planets. Some of them travel enormously far from the Sun before returning inward again. They preserve a memory of disturbance. They remind us that the outer solar system is not only a storage zone of ancient bodies, but also a record of how those bodies were thrown, trapped, and redistributed. Some objects escape the distant icy reservoirs and move inward toward the Sun. When they do, we often call them comets. Comets are among the most dramatic leftovers in the solar system, but their drama appears only when they approach the Sun and begin to warm. Their ices start to vaporize, carrying dust away and creating the glowing coma and tail that make comets so distinctive in the sky. Yet beneath that display, a comet is essentially an ancient body of ice, dust, rock, and organic-rich material preserved from the dawn of the solar system. That is why comets are so important. They are not only beautiful visitors, they are cold storage samples of early solar system material. Because many of them spent most of their history far from the Sun, they can preserve substances and structures that would not survive in warmer regions. Some scientists think comets may have helped deliver water and organic compounds to the young Earth, though the full story is still complex and depends on the kinds of bodies involved. Even where the details remain debated, comets clearly connect the distant outer reservoirs to the inner worlds. Not all comets come from the same place. Many short-period comets are thought to originate in the Kuiper belt or the scattered disk. Long-period comets, by contrast, are linked to the Oort cloud, one of the most distant structures associated with the solar system. The Oort cloud is thought to be a vast spherical shell of icy bodies surrounding the planetary region at enormous distances. It is so far away that no object in it has been directly imaged in detail as a member of that cloud, but its existence is strongly inferred from the orbits of long-period comets. The Oort cloud is especially revealing because it shows just how much material the young solar system scattered outward. The giant planets, especially Jupiter, likely flung countless icy bodies into distant space. Some escaped the solar system entirely. Others were stranded on large orbits, where passing stars and galactic tides helped shape them into a more spherical cloud rather than a flat disk. In that sense, the Oort cloud is another graveyard of leftovers, built by planetary scattering on an enormous scale. Taken together, the asteroid belt, the Kuiper belt, the scattered disk, the dwarf planets, the comets, and the Oort cloud all tell the same broad story. Planet formation did not use up all the available material. It left behind layers of memory. Some leftovers stayed close to the sun, some remained beyond the giant planets. Some were tossed into remote darkness. Each population preserves a different piece of the solar system's childhood, and perhaps the most beautiful part of this is that the leftovers are not unimportant simply because they are small. In some ways, they are more informative than the planets themselves. The major planets continued evolving for billions of years. Their surfaces changed, their atmospheres shifted, and their interiors developed. But many smaller leftover bodies remained far more primitive. They preserve older conditions, older chemistry, and older structural clues. They are like pages torn from the earliest draft of the solar system and never fully rewritten. So this chapter of the story is not about failure, it is about survival. These bodies never became planets, but they endured. They remained in the gaps, the belts, the distant fringes, and the cold outer dark. And because they remained, they still carry the record of a time before the solar system settled into its modern calm, when worlds were still assembling and not every fragment found a permanent home. Chapter 9. How Earth became a living world in a dangerous system. Earth did not begin as a gentle blue world ready for life, but as a hot, battered planet inside a solar system that was still full of violent change. By the time the major planets had taken shape and the giant planets had helped rearrange the system, Earth already existed as a young rocky world orbiting the sun at a very fortunate distance. But being in the right general location was only the beginning. A planet can orbit in a favorable zone and still become lifeless, frozen, or unrecognizable. Earth became a living world because several conditions worked together over a very long time, and because the planet managed to remain stable enough for life to begin and resilient enough for life to continue. Early Earth was not calm. It was still releasing heat from its formation, still feeling the effects of massive impacts, and still building the atmosphere and oceans that would eventually make biology possible. The surface was probably covered in vast areas of molten or partially molten rock during the earliest stages of its history. Volcanoes were common. Material from space still struck the planet. The young sun was also more active than it is now, producing stronger solar winds and bursts of energetic radiation. Earth was not born safe. It became habitable while danger was all around it. One of the most important steps in that transformation was cooling. A world cannot support stable oceans or long-lived surface environments for life if its surface remains largely molten. As the young Earth radiated heat into space, its outer layers solidified and a more persistent crust began to form. This was not a single clean transition. Impacts could remelt parts of the surface, and internal heat continued driving volcanism from below. But over time, the planet moved away from its most extreme early state and toward something more geologically structured. As Earth cooled, gases released from its interior helped build the early atmosphere. This first atmosphere was not like the air people breathe today. It was shaped by volcanic outgassing and probably contained large amounts of water vapor, carbon dioxide, nitrogen, and other gases. Free oxygen was not yet an important component. The atmosphere of early Earth was therefore not the product of life. It was the background against which life would later emerge. Water was central to everything that followed. The exact origin of Earth's water is still an active scientific question, but the broad picture is that Earth likely acquired water from more than one source. Some may have been incorporated into the planet during its formation. Some may have arrived later in water-rich bodies from farther out in the solar system. What matters most for the story of habitability is that Earth ended up with enough water and with conditions cool enough for stable oceans to form. Once the surface cooled sufficiently and water vapor in the atmosphere could condense, the planet gained something extraordinary: long-lived liquid water on its surface. That changed the entire trajectory of Earth. Water is not just important because living things need it. Liquid water also reshapes rocks, moves heat, dissolves and transports chemicals, and helps connect the atmosphere, crust, and interior into one interacting system. Oceans store and redistribute energy. They soften temperature extremes. They provide settings where chemistry can proceed over long spans of time. In the deep past, they may also have offered some protection for early life from the harsher radiation environment of the young sun. Even with oceans, however, Earth could still have failed as a habitable world. Early in its history, the sun was dimmer than it is now. That might seem to imply that Earth should have been frozen. Yet geological evidence shows that liquid water existed on Earth very early. The likely explanation is that Earth's atmosphere contained greenhouse gases that trapped enough heat to keep the planet from freezing over completely. In other words, habitability depended not only on distance from the sun, but also on atmospheric composition. This is where Earth's long-term climate regulation became crucial. Over immense spans of time, carbon moved through the atmosphere, oceans, rocks, and interior in what we call the carbon cycle. Carbon dioxide in the atmosphere warms the planet. Rain and ocean chemistry help remove carbon from the atmosphere through weathering and the formation of carbon-bearing minerals. Some of that carbon is carried into the crust and eventually returned by volcanism. This slow exchange acts like a planetary thermostat. If the planet becomes warmer, weathering tends to increase, which helps draw down carbon dioxide. If the planet becomes colder, weathering weakens, allowing volcanic carbon dioxide to build back up. It is not a perfect control system, but over geologic time, it helps prevent the climate from swinging permanently toward either extreme. Earth's interior made that possible. A geologically dead planet cannot recycle material the same way. Earth remained internally active for a long time, because it was large enough to hold heat and because radioactive elements inside it continued releasing energy. That internal heat drove mantle motion, volcanism, and eventually plate tectonics. Plate tectonics is one of the deepest reasons Earth has remained habitable for so long. It recycles crust, reshapes continents and ocean basins, helps regulate the carbon cycle, and creates diverse chemical environments at the surface and seafloor. Earth is not habitable simply because it sits in the right place. It is habitable because it is an active planet. Its magnetic field also seems to have mattered, though scientists still study exactly how much. Earth's magnetic field is generated by motions in the liquid outer core, where electrically conducting material moves and creates a global magnetosphere. This magnetic shield deflects charged particles from the solar wind and helps reduce the direct stripping of the atmosphere by solar particles. The full relationship between magnetic fields and atmospheric preservation is complex, but there is strong reason to think that Earth's magnetic field contributed to the long-term protection of the planet's environment. At the very least, it changed how the upper atmosphere interacted with the young sun. The moon may also have played a quiet but important role. It did not create Earth's habitability by itself, yet it likely helped steady the planet's axial tilt over long periods. That matters because large chaotic swings in tilt can produce more severe climate instability. The moon also raises tides, and tides do more than move shorelines. They influence ocean circulation, stir coastal environments, and connect celestial mechanics to the chemistry of the sea. In Earth's early history, when the moon was closer than it is now, those tidal effects were even stronger. But stability never meant safety. Earth remained inside a dangerous system. Impacts from asteroids and comets continued long after the planet formed. Some were destructive enough to melt crust, boil regional water, or alter climate. Over time, the overall bombardment rate fell, and that decline was essential. A planet cannot easily develop and preserve continuous habitable environments if it is constantly being sterilized by giant collisions. Earth's history became more favorable not because danger disappeared, but because it became less overwhelming. At the same time, some dangers may also have brought opportunities. Incoming bodies could deliver water, organic compounds, and chemically useful material. Impacts can be devastating, but they can also create new environments such as hydrothermal systems, fractured crust, and temporary chemical niches. The same solar system that threatened Earth also supplied some of the ingredients and energy-rich settings that may have helped life get started. Exactly where life began on Earth remains unknown. Several plausible settings have been proposed. Some scientists focus on shallow surface environments, where wetting, drying, and mineral surfaces could have helped organize complex chemistry. Others point to hydrothermal environments on the ocean floor, where water, heat, and chemically reactive minerals meet. What matters here is not choosing one final answer, but understanding the kind of planet Earth had become. It had liquid water, persistent energy sources, active geology, abundant chemical cycling, and enough long-term stability for chemistry to explore increasingly complex possibilities. Once life began, Earth changed again. Biology did not merely adapt to the planet, it started reshaping the planet. Microbes altered chemical cycles. Later, photosynthetic organisms transformed the atmosphere by releasing oxygen. Over immense spans of time, life and planet became inseparable. The surface of Earth today is not just a physical environment that happens to contain living things. It is a world whose air, oceans, soils, and rocks have all been modified by living processes. That is perhaps the deepest answer to how Earth became a living world in a dangerous system. It was not because one single factor protected it from all harm. It was because many systems lined up well enough and kept working long enough for habitability to persist through danger rather than in the absence of danger. Earth had the right amount of gravity to hold a substantial atmosphere, enough internal heat to remain geologically active, enough water to form oceans, enough climate regulation to avoid permanent catastrophe, and enough protection to endure the harsher behavior of the young sun. It was helped by the moon, shaped by impacts, and sustained by deep planetary processes hidden beneath the surface. In the end, Earth did not become alive because the solar system was gentle. It became alive because one small rocky planet managed to find a lasting balance inside a system that could easily have gone another way. The asteroids still crossed the inner solar system. The sun still sent out storms. The planet itself still erupted, shifted, and changed. But between all those forces, a narrow but durable window stayed open. Oceans remained, chemistry deepened, life began. And once life appeared, Earth was no longer only a planet, it became a living world. Chapter 10. The Future and Final Fate of the Solar System. The solar system that now feels so steady and familiar is not permanent, because the same sun that gave it warmth and order will eventually change in ways that no planet can ignore. For human lives, and even for the whole span of recorded history, the solar system appears almost unshakably stable. The planets keep their paths. The sun rises with reliable brightness. The distant giant planets move with a patience so great that their slowness feels almost eternal. But astronomy teaches a different lesson. Stability is real, yet temporary. The sun is a star, and stars evolve. That single fact means the solar system already contains its own ending. Right now, the sun is in the long central phase of its life, steadily fusing hydrogen in its core. This stage lasts for billions of years, which is why the sun seems constant on human timescales. But it is not truly unchanging. Very slowly, as hydrogen in the core is converted into helium, the internal structure of the sun shifts. Over time, the sun becomes brighter. The increase is gradual, but on geological timescales, gradual does not mean small. It means unstoppable. That brightening matters because habitability depends not only on where a planet orbits, but also on how much energy its star gives off. Earth is habitable now because the balance between incoming sunlight, atmospheric chemistry, oceans, clouds, and geology still allows liquid water to remain stable at the surface. But that balance will not last forever. Long before the sun enters its most dramatic final stages, Earth will begin losing the climatic conditions that made it a living world. As the sun slowly brightens, Earth's surface will warm. At first, this may sound like only a stronger version of present conditions, but over immense spans of time, the consequences become profound. Higher temperatures speed up the weathering of rocks, and that process pulls carbon dioxide out of the atmosphere. Carbon dioxide is also essential for photosynthetic life as we know it. As the sun grows brighter, the atmospheric carbon dioxide available to complex plant life will likely fall. In other words, the decline of habitability may begin not with oceans suddenly boiling away, but with the weakening of the biological and chemical systems that support the modern Earth. Much farther along, warming becomes more severe. Oceans evaporate more easily. water vapor rises higher into the atmosphere. Because water vapor is a greenhouse gas, this traps more heat and drives further warming. At a certain point, the balance tips too far. Earth enters a moist greenhouse or runaway greenhouse path in which its water is progressively lost. Once the oceans are gone or greatly reduced, the planet is transformed. The blue world becomes a hot and drying world, then a barren one. This future does not wait until the sun becomes a red giant. Earth is expected to become uninhabitable well before that. In terms of life as we know it, the end comes earlier than the final stellar catastrophe. The planet may remain physically present for a very long time, but the conditions that allow oceans, complex ecosystems, and a breathable atmosphere are temporary features of a middle chapter, not permanent properties of the Earth. Meanwhile, the outer planets will still be circling in deep cold, and the smaller leftovers of the solar system will continue their long orbits. But the central change driving everything will remain the same. The sun is running through its fuel. Eventually, the hydrogen in the core becomes too depleted to support the present balance between gravity pulling inward and pressure pushing outward. The core contracts, temperatures rise, hydrogen fusion shifts into a shell surrounding the core. The outer layers of the sun respond by expanding enormously. This is the beginning of the red giant phase. The sun will swell outward and become vastly larger and more luminous than it is now. Its surface will be cooler in temperature than today, which is why red giants appear redder. But the star as a whole will pour out far more energy because of its enormous size. To any surviving world nearby, the red giant sun would dominate the sky. Mercury will not survive this transformation. Venus will not survive it either. Both of these inner planets lie too close to the sun to escape engulfment as the solar atmosphere expands outward. Their long histories will end inside the dying star that once illuminated them. Whether Earth itself is swallowed remains more uncertain, but the outlook is grim. As the sun loses mass, Earth's orbit is expected to drift outward to some degree because the weakened gravitational grip allows surviving planets to move farther away. Yet tidal interactions between the swollen sun and Earth can also pull the planet inward. Current scientific understanding leaves Earth's precise physical fate uncertain, but even the most favorable possibilities do not leave it habitable. By then, Earth would already have been sterilized, its oceans gone, its surface transformed beyond recognition, and its atmosphere profoundly altered or stripped away. Mars, if it still survives as a physical world, may for a time receive more warmth than it does now. Some icy bodies in the outer solar system may also experience temporary warming. There is a strange irony in that. Regions now frozen and dim could briefly pass through milder conditions while Earth and the inner worlds are being destroyed. But this would not be a new stable age of life for the solar system. It would be a temporary consequence of stellar death, not a fresh beginning. The red giant phase itself is not a single quiet swelling. The sun's internal structure will continue changing as fusion processes shift. After the core contracts and heats further, helium fusion will begin in the interior. Later stages follow, but for a star like the sun, they do not continue indefinitely toward heavier elements. The sun is not massive enough to end as a supernova or a black hole. Its death is gentler than that, but only by stellar standards. For the planets, it is still catastrophic. As the sun nears the end of its giant phase, it will shed a large fraction of its outer layers into space. These expanding shells of gas will drift outward and glow when illuminated by the hot, exposed core left behind. This creates what astronomers call a planetary nebula, a beautiful and misleading name from the early history of telescopes. It has nothing to do with planets being born. Instead, it is the visible farewell of a dying sun-like star casting off its atmosphere. At the center of that expanding nebula, the sun's remnant core will remain. This leftover core will be a white dwarf. A white dwarf is not powered by new fusion. It shines because it is still intensely hot from its earlier history, and because it is extraordinarily dense. Our sun will end as a stellar ember roughly the size of Earth, but containing much of the sun's former mass. By this point, the solar system will be unrecognizable. The inner planets will be gone or ruined. The giant planets, if they survive as expected, will orbit farther from the white dwarf than they once orbited from the sun because of the mass the sun lost during its giant phase. Their moons, rings, and atmospheres will continue to evolve under a much weaker and steadily fading light. The asteroid belt will be depleted and disturbed. Some smaller bodies will have been swallowed during the sun's expansion. Others will have been destabilized by the shifting gravitational architecture of the dying system. And yet the story does not fully end even there. Observations of other white dwarf systems suggest that planetary remnants can persist for very long times. Giant planets may survive. Asteroids and icy bodies can remain on distant orbits. Some of these leftovers may later be perturbed inward, torn apart, and ground into dusty disks around the white dwarf. So even after the sun is dead in the ordinary stellar sense, the remains of the solar system may still interact, collide, and slowly rearrange themselves. The white dwarf itself will cool for billions upon billions of years. It will not suddenly switch off. It will fade gradually, radiating away stored heat into the darkness. With time, the solar system will become dimmer, colder, and quieter than anything we now experience. The worlds that remain will no longer be lit by a life-giving star. They will circle a fading remnant under a blacker sky. On even longer timescales, the outermost reservoir of the solar system will also continue to change. Passing stars, the gravity of the Milky Way, and rare encounters over immense spans of time can disturb distant comets and the farthest leftovers. Some objects will be ejected into interstellar space. Some may fall inward. Some may continue orbiting a dead sun for durations that are difficult for the human mind to picture. The solar system's final state is therefore not one single moment, but a long fading afterlife. So the future of the solar system is not an abrupt stop. It is a sequence of endings. First, the loss of Earth's habitability under a brightening sun. Then the red giant transformation that destroys the inner system. Then the casting off of the sun's outer layers into space. Then the white dwarf age, in which surviving outer worlds circle a cooling stellar core. And after that, a deep future of slow erosion, scattered debris, and fading light. There is something solemn in that, but not necessarily frightening. The solar system was never promised permanence. It was a temporary arrangement of matter around a middle-aged star, beautiful because it changed, and meaningful because it had seasons in time. The same story that gave rise to planets, oceans, atmospheres, and life also contains decline, loss, and stillness. One day the sun will no longer be the bright anchor of our sky. But even then, the history written by its light will remain part of the larger history of the galaxy, where stars continue to form, evolve, and fade in their turn. And that, my friend, is the story of our solar system. I hope this journey helped your mind slow down and carried you gently away from the noise of the day. If you are still awake, you can stay with me a little longer and choose another video to drift off to. And if not, then sweet dreams among the stars.